Hey guys, today we're going to look at 3.4, which is going to talk about linear and angular speed. So linear speed is going to talk about how fast a point is moving around a circle, whereas angular speed is going to talk about how fast the angle is speeding, like up or moving as that point is going around the circle. So linear speed is the point moving around the circle. Angular speed is how the angle changes as that point moves around the circle. If I'm looking at linear speed, we've got a couple different ways that we can represent this formula. Remember, speed is distance over time. So you could quite literally just say that it's d over t. We got to talk about what that distance is, though. So if we're talking about it going around a circle, that's the circumference or part of the circumference, which lucky for us, we talked about in our 3.2 notes, part of the circumference is what we call an arc of a circle. And we have a formula for that. An arc length formula, remember we talked about it as S instead of V, but our arc length formula is r theta. So our distance is our arc length. So d is the distance, which is an arc length, which is that S equals r theta formula that we talked about in the 3.2 notes. So that's how we get to our second version of it, which is V is equal to r theta over t. Now, the last way that we can represent it is V is equal to r times this W, which is our angular speed. Our angular speed is theta over t, so it's just taking that theta over t part of our r theta over t and making that r times W instead of r times theta over t. So what you want to look at is what information you're given in the problem, and that'll kind of help you determine which of those three versions of the linear speed formula you want to use. Angular speed, though, just has the one W equals theta over t. Now, what's really, really important is that your theta, your angle, does have to be in radians. If you haven't picked up on that, all of chapter 3 right here, 3.1, 3.2, 3.3, and 3.4, all dealing with radians. So our angle does need to be in radians. So let's look at some examples here. Our first example says, suppose that point P is on a circle with a radius of 10 centimeters, and ray OP is rotating with angular speed of pi over 18 radians per second. We have three questions we're going to answer about this. Now, what's tricky about these problems is figuring out what you're trying to find and figuring out what you need to plug into what formula, not necessarily like the actual math that you're doing. So you're going to have to read a little bit and actually figure out what you're plugging in, where you're plugging it in, which formula to use, all that kind of stuff. So part A says find the angle generated by P in 6 seconds. Leave your answer in terms of pi. So if it says find the angle, that means I'm trying to find my theta. Okay, I need to look at the information that it's given me. So over here, it's given me 6 seconds. So that's going to be my t. And we did have some information up at the top here that it gave me. It gave me a radius of 10 centimeters. So I can say that r is equal to 10. And it also told me my angular speed was, excuse me, pi over 18. So that's my w is equal to pi over 18. So if I know angular speed, that's probably the formula I want to start with. I don't know anything about linear speed here, but I do know my angular speed, so I can use that formula to help me work backwards and find my theta. So our angular speed formula is that W equals theta over t. So I'm going to come write that down over here. And if you look, we also know our t, our time. So I can plug all of that into my equation. My angular speed, W, is going to be that pi over 18. It's going to equal the theta that I'm trying to find divided by the time that they gave me, the 6 seconds. So all I have to do here to figure out what my theta is multiply both sides by 6. Okay, that gets me that theta is equal to 6 pi over 18. I can't leave it like that though. I do want my answer in terms of pi, but 6 pi over 18 does simplify. So theta is going to simplify down to pi over 3. We are talking about radians, so you don't technically need a unit here, but if you really feel like upset about not writing something, you can write radians behind it if that makes you feel a little bit more comfortable. Okay, then part B says find the distance traveled by P along the circle in 6 seconds. Leave your answer in terms of pi. So we were kind of talking about it up there. When I'm talking about distance, that's the D that's in my formula, D for distance. And if you look right here, I wrote out that your distance is your arc length, your S equals R theta. So I'm going to say that my distance is equal to R times theta. Well, it told me my radius up here, and I just found a theta right here that matches up with 6 seconds, and what we're looking at right here is also 6 seconds. So I can use that theta again, so I'm just going to plug what I know into my equation. So my distance is going to be my radius, which is that 10 centimeters, times the theta that I just found, that pi over 3. Once again, it says leave your answer in terms of pi, so my distance is going to be 10 pi over 3. And my units here, if our angular speed, talking about radians per second, that doesn't really help me, but it did say my radius was 10 centimeters, so that does help me. My distance is 10 pi over 3 centimeters. So you also need to make sure you're reading to help give you the context clues for what your units need to be. Then my last part says find the linear speed of p in centimeters per second. Leave your answer in terms of pi. Now remember, we got 3 different options for linear speed. We just found d, the distance, so I'm probably going to use the formula that has d in it. Or, if you notice, they gave me here my radius and my angular speed, so I could use the formula that just multiplies the radius times the angular speed. You got different options here. The safe bet is to use that bottom one that does the radius times the angular speed, because that's the information they gave you in the problem. So if you did make a mistake in part A or part B, then your part C wouldn't be wrong because you're using given information instead of using something you found in a different part. So let's use that one. I'm going to come down here and I'm going to say my linear speed is equal to R times my angular speed. My radius was 10. My angular speed was pi over 18. So it's going to be 10 pi over 18. I do need my answer in terms of pi, but I can't leave it like that. I've got to simplify it. So my 10 over my 18 does simplify down to 5 pi over 9. And it does tell me my units right here in the problem, centimeters per second. Find the linear speed of p in centimeters per second. Centimeters per second. Which also you could look at our problems and notice that part B was talking about centimeters. Also looking up here, we talked about seconds here and seconds here. So you could also use your context clues in the other parts to lead you to that centimeters per second for your units. And that's example 1. We got 2 more that we're going to look at. So let's look at example 2. A belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. Part A says find the angular speed of the pulley in radians per second and leave your answer in terms of pi. So if we're talking about a belt running a pulley, the easiest thing that I can think of to explain it is like think about a treadmill and how like that's a belt that's moving that you run on. And so there's a um, like a pulley system that moves that belt. So the belt runs the pulley. It's got like a circular thing that's moving to make that treadmill run. So a belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. If I'm trying to find the angular speed, we've only got one formula for that. So my formula is W equals theta over V. Now, if I'm looking at this, they didn't really give me a theta or a time in my problem. And also, if I'm looking at this, you may notice that up here it talks about revolutions per minute, but down here it wants my answer in radians per second. So we're going to have to do a little converting of units. So let's kind of think a little bit. Let's start with the theta. I need an angle. That 80 revolutions per minute is going to help me figure that out. If I think about the word revolutions, that word revolutions means revolving, going around the circle. A revolution goes all the way around the circle. So one revolution means that I have an angle that's 2 pi going all the way around the circle. The problem is I have 80 revolutions. So to find my angle, if I have 80 revolutions, that means I need to do 80 times that angle for one revolution, which is 2 pi. So 80 revolutions, 80 times 2 pi is 160 pi. So 80 revolutions gets me an angle of 160 pi. It means I'm going around the circle 80 times. So around the circle once is 2 pi, around the second time is 4 pi, then 6 pi, then 8 pi, and keep going around 80 times. So 160 pi is my angle. And when I'm talking about my time, we're going from minutes to seconds. So 1 minute is equal to 60 seconds. So that's going to be my time here, 60 seconds. I take that 160 pi divided by 60. It does say to leave your answer in terms of pi, but I do need to simplify that. And so I end up with 8 pi over 3 radians per second. So, like I said, the actual math you're doing wasn't too complicated. 160 pi over 60, just simplifying that fraction. But you did have to read and kind of think about, what does a revolution mean? Read and look and see that it went from minutes to seconds. You've got to make sure you're paying attention to the problem. Okay, part B says find the linear speed of the belt in centimeters per second. Leave your answer in terms of pi. So remember, we've got a bunch of different options for the linear speed equation. I just found the angular speed, so I'm going to use that equation that has the angular speed in it. So that's the V equals R times my angular speed, W. R is the radius, W is the angular speed. And look at that, it gives me a radius. My radius is 6 centimeters. The angular speed I just found is 8 pi over 3, and it is in seconds, and we are looking in centimeters per second. I don't have to worry about converting again. So I just multiply those together. 6 times 8 pi over 3 is going to give me 48 pi over 3, which simplifies to 16 pi centimeters per second. There is our answer for part B. Now let's look at our last problem. Example 3, a satellite traveling in a circular orbit 1,600 kilometers above the surface of Earth takes 2 hours to make an orbit. The radius of Earth is approximately 6,400 kilometers. Ooh. Approximate the linear speed of the satellite in kilometers per hour. Leave your answer in terms of pi. So approximate the linear speed. We're finding linear speed. Now, we don't know the angular speed here. We don't know a d, a distance, or anything. So that means when I'm looking at this for my linear speed, I want to use that v equals r theta over t. Because I don't know the angular speed to be able to plug it into the formula, and I don't know an arc length. So I need to have that formula built into my equation already. That r theta needs to be in there because I don't know d yet. I don't know the distance. So when I'm plugging all this in, I need to know a radius, a theta, and a time. If I'm looking at my problem, there is a nice little picture here, and that does kind of help us figure out what our radius is going to be. If I look, it's labeled here for us, and you can see they kind of show you that you've got this little section and this little section that together make up the whole radius. So to find my radius, I'm going to do 1,600 for how far it is above the Earth's surface, plus the 6,400 that goes from the center of the Earth to the Earth's surface. When I add that together, I get 8,000. So my radius is 8,000 kilometers. Okay, now I got to figure out my theta and my time, which I can come up here and I can see it takes 2 hours to make an orbit. That helps me a little bit with my time. That's going to be 2 hours. And then if I'm talking about an orbit, a full orbit is going all the way around the Earth, all the way around the circle. So one orbit is equal to 2 pi for its angle. So my theta, once again, is all the way around the circle, 2 pi. So plug it all in. Let's see what we get. So V is going to equal that 8,000 times my 2 pi divided by my 2. And what you notice here is that the 2 in the 2 pi and the 2 in the denominator do actually cancel out. So my answer is just 8,000 pi. And my unit is kilometers per hour. So there we go. And the last part says approximate the distance the satellite travels in 4.5 hours. Leave your answer in terms of pi. So if I'm looking at this, if we're talking about approximating the distance, oh, that's not the highlighter. There we go. Remember, we talked about how distance is like an arc length. We can use V equals D over T. It tells us our time right here, 4.5 hours. If I'm trying to find my distance, I'm trying to find my D. And then my V, I just found in part A. So I'm going to have 8,000 pi is equal to my distance that I'm trying to find divided by the 4.5 hours. So to figure out the distance, I would just multiply both sides by 4.5. 4.5 times 8,000 pi, leaving your answer in terms of pi means I would really just do the 4.5 times 8,000. So that's going to get me that my distance is 36,000 pi. And then it is just a distance, so it's no longer kilometers per hour, it's just the kilometers part. It's just the distance. And there we go. That's our notes for linear and angular speed. Okay, if you have any questions, let me know. Make sure you get started on your assignment that goes with this set of notes, and y'all have a good day.